Hello, everyone. We just wait a few minutes for that people connected. I think we can get started, right? So, hello and welcome, everyone. We appreciate you taking the time to participate in this section. Today's webinar is to introduce the tool for quantifying organic carbon stocks using digital soil mapping. With the ID number of this tool is CN0137. My name is Carolina Lisboa, and I will be your host today. Before we dive in, let's take care of a few housekeeping items. This section will last about 60 minutes, and we encourage you to engage with us throughout. Feel free to drop your questions in the Q&A section box, and we will address them during the discussion, the webinar presentation, and also at the end, we will answer some few questions alive. The record will be available online on the Verra website and also in the Verra YouTube channel. The webinar today will be presented by Perennial Climate, who is the developer of this tool. And we have two speakers from the presentation. We have here Jim Kellner and David Sherman. So, the webinar today has three sections. We start with an overview of the methodology development review process. Then we move to Perennial, and they will give you an introduction to the CM0137, the draft tool. And then we close with a Q&A section. As part of the verified carbon standard documentation, we have a specific guidance for methodology development under the VCS program. You see here to the left is the first page of this document, which is the methodology development and review process. This document set out the procedures and the rules for developing methodologies under the VCS program. Any proposed new methodology or modules or tools are developed through the process set out in the MDRP. Here to the right, you see the main steps of this process. There are in total 6 steps. Start with methodology idea note submission, methodology concept note development, draft methodology development, step 4, public consultation, step 5, methodology assessment, step 6 as a final Verra review and the final decision. Specific to this tool, I want to mention that this started by the end of 2021, when Perennial first approached Verra to propose their idea. And then in the beginning of 2022, they submit the concept note development, their concept note. And then this concept note went through several rounds of reviews from Verra. And after more or less 2 years of rounds of reviews, Verra finally approved the tool to move to step 3, to the draft of the tool development. And then Verra also at this time requests that Perennial would establish a working group to give critical feedback to the draft. And we are now then on the step 4, public consultation. This public consultation was launched a few weeks ago, to be more precise, on February 20th, and it's going to run until April 4th. And we are accepting your feedback throughout. You can submit your feedback in an electronic form, which is online on the Verra web page. And I will ask my colleagues to make sure that we share the link with you to access this form. With that, I will let welcome our speakers and hand over to you, Jim. Thank you.
Thank you very much, Carolina. I'm going to ask my colleague David Sherman to introduce himself in just a moment. I'd like to begin by introducing myself. My name is Jim Kellner, and I'm the Chief Scientist for Perennial Climate Incorporated. I'll be walking you through the presentation today and explaining the process of digital soil mapping, the decisions that we've made, and it's very important that I give you a clear understanding of how we got to the point where we are. I want to be able to justify the decisions and give you the confidence to be able to go into the tool document itself and understand how this thing works so that you can provide us with the feedback necessary to make any changes needed in order to facilitate your own use and success. David, would you like to say a few words?
Yes, thank you, Jim. Hi, everyone. I'm David Sherman, one of the co-founders of Perennial. My background is mostly in climate sciences, earth and environmental sciences, and scientific computing, focused on those domains. And what I wanted to say before handing it off to Jim for the rest of the presentation is we are truly extremely excited to be bringing this to you. This represents thousands of hours of work. This represents over 3 years of development. And this has been looked at by now dozens of independent experts. And we feel that it really reflects the scientific community's consensus of how to do this in a way that is robust. And we're proud of it. We are excited to hear your feedback, and we're looking forward to walking you through it a little bit and showing you a little bit of how this works and why we made the decisions that we made. Back to you, Jim.
Great. So I'd like to begin by focusing on how the thing came together. It was developed by Perennial in consultation with a group called Terra Carbon. And I want to give a specific mention here to my colleague Jacqueline Ketchelmeyer at Terra Carbon. She works on the agricultural team there and worked with us on the development of the original concept note and all the way through the development of the tool text. Jacqueline has expertise in the development of VCS methodologies. She's contributed to earlier versions of VM42 and also to the revisions of VM. Somebody needs to mute, please. Thank you. Also, there is to the revisions of VM42 version 3. During the process of development, we used what was called a working group structure. So after the original concept note was drafted and sent to Verra, Verra provided feedback that included some expert external review, and that led to a decision to create an independent working group. The working group was handled outside of Verra, and the process was run by Perennial. And the idea here was to bring together a group of people that represented academic expertise, industry expertise, private companies, and also one VVB, a validation and verification body. We wanted to have viewpoint from people who might use the tool and who have an interest in the application of the tool from the widest possible range of perspectives. There's geographic diversity in here. We had people from Brazil, people from Europe, people from Australia, people from North America. We have people who work in smallholder situations, people who work in East Africa, people who work in India, people who work in large row crops. The idea was to ensure that the ideas that are represented in this document have been tested, so to speak, out in the real world, so that we're developing something that is going to be truly useful for everyone to be able to use. The process began in February 2022, as Carolina described, so we're now more than 3 years in. If you could advance to the next slide, please, Carolina, I'll introduce the members of the core group. So the way we set this up was in a kind of bifurcated approach. There was what we called the core group, and these were the people with ultimate responsibility for making decisions and writing the document. And then there was a much larger advisory group, and I'll talk about them in a moment. I'd like to just describe who was on the core group here. Number one was Dan Kane. Dan is currently at Mad Agriculture, formerly at Terra Carbon. Dan has a PhD from the School of Forestry and Environmental Studies at Yale, and he's part of the team that developed and revised VM42. Brian McConkey is the chief scientist for Varesco Solutions. He has more than 35 years of agricultural and environmental research experience in Canada. He's played a leadership role that has influenced Canada's national greenhouse gas inventory, and he has published a ton of papers and also is a contributor to VM42. Sasan Sachi is a remote sensing scientist at the Jet Propulsion Laboratory and Caltech. Sasan has expertise in remote sensing of forest carbon, and he was one of the original authors of a different Verra tool called VT5, which is the tool for above ground live forest biomass using different kinds of remote sensing. So Sasan has expertise in both the spatial prediction problem and the remote sensing problem applied to a slightly adjacent situation here within Verra. Jonathan Sanderman has a PhD and is a director of the carbon program at Woodwell Climate Research Center. He focuses on the role of science in climate mitigation and sustainable food production and has published a very large number of high-profile papers that underpin the legitimacy of nature-based climate solutions. Finally, Alex Wadu is a fellow at the French National Institute for Agriculture, Food, and Environment in France. He's an expert in the field of digital soil mapping and specifically in the applications of geostatistical methods, which I'll talk about in a few moments, to digital soil mapping, including, very importantly for the tool, the issue of error propagation and how you calculate uncertainty. Carolina Lisboa, who we met just a few moments ago, also participated in the core group as an observer from Verra. The next slide discusses the advisory group. The advisory group was a very wide range of scientists and industry participants with expertise from around the world. I've already mentioned to you that we specifically focused on curating a group here that has geographic expertise, disciplinary expertise, people who work in row crops, people who work in more boutique situations, people who work in smallholder farms, people who work in very large farms. It was very important to us that the tool be developed in a way that doesn't just serve one region of the world or one agricultural situation. And we specifically sought critical feedback from people who worked in a variety of conditions so that we could learn at the development stage what things might need to be modified or changed in order to allow the tool to be useful in all the situations that all of you may have an interest in. And we think we've implemented those changes along the way so that the tool is now useful to everybody. We specifically, however, seek additional feedback on this issue, and we'd love to hear from you about ways you think it is aligned or could be changed to be compliant with your interests. The advisory group includes scientists, private companies, and also I've mentioned a VVB. The private companies included technology companies, project developers, and a very wide range of individuals with an interest in nature-based carbon solutions more generally. If you can go to the next slide, please. So what the tool is focused on is bringing the discipline of digital soil mapping, or what we call DSM. You might hear me use that acronym, DSM, to the problem of quantification in compliance with VCS carbon programs. Digital soil mapping is a mature technology. It's supported by thousands of peer-reviewed academic articles over a series of decades. There's an appendix in the tool, Appendix 3, where we highlight specifically a sample of these publications. And what we tried to do there was highlight examples that illustrate applications of digital soil mapping using a very wide range of measurement approaches, sensors, data sets, statistical methods, to illustrate to you the diversity of ways in which digital soil mapping may be applied under a VCS carbon program. We designed the tool to provide guidance on how to use digital soil mapping for VCS carbon projects. And specifically, we're focused on how do you calculate soil organic carbon, that's SOC stocks, and how those stocks are changing over time. How do you do that in a way that is rigorous? And we provide guidance on how to calibrate, validate, and deal with uncertainty estimation. Before we go to the next slide, I want to say here that one of the guiding principles we adopted was the idea that the approach in the tool should be flexible. We are trying not to be overly rigid in telling you exactly how to do this. So for example, we provide guardrails and we have outcome-based criteria for judging whether a digital soil mapping model is good enough or not. That's different from trying to compel you to adopt certain kinds of inputs. So there's a very wide range of statistical procedures that are compliant with the tool. It's up to you to decide. We provide guidance, but it's up to you to decide what kind of statistical model you might want to use, what kind of data sets you might want to assimilate into that statistical model. We give suggestions. We provide pointers on things that have worked for other people, but we want to be open to creativity and innovation. And by imposing the requirements in the tool on the output, that's how we ensure rigor, rather than being overly concerned with the input. It's not that there's no concern with the inputs at all, but that inputs without a high quality output don't get you what you really want. And I'll describe to you 3 tests in a few moments that allow us to prove that the tool really is doing what it's supposed to do with rigor. If you can go to the next slide, please. These next 2 slides, the next slide, please. Thank you. These next 2 slides are just to demonstrate to you that the field of digital soil mapping is a mature discipline. What I did here was I pulled down peer-reviewed academic publications that have been published within the field of digital soil mapping. There's more than 5,600 of them. I then grouped them into categories, and I'm just trying to illustrate to you the diversity of what is out there. Not all 5,661 are shown on this graph because they're smaller categories, but what you can see, for example, is 1,500 of these papers appear in the field of soil science. There's another several hundred in the field of remote sensing, 1,380 in the environmental sciences, just under 300 in the field of agronomy, and so on, 232 in ecology. The point is that this is a technology that has been applied across a very wide range of disciplines to a very wide range of problems over the last several decades, resulting in the more than 5,600 publications to date. The next slide shows geographic representation. If you could go to the next slide, we'll see that. The purpose of this next slide is simply to illustrate that the field of digital soil mapping has been active all around the world. There are examples just on this slide, and again, not all categories, not all geographies are shown because the smaller ones don't show up, but you can see there's examples from North America, from Asia, from Europe, from Australia, from South America. Not shown on the slide are some applications on the continent of Africa. Every continent that has agriculture has had digital soil mapping, and there is an active body of research and individuals working on the field of digital soil mapping in each of these locations all around the world, justifying the maturity of the technology and its readiness for VCS carbon programs. Next slide, please. I want to give people a feel for what the outcome of digital soil mapping looks like. We're going to walk through the process of how one uses digital soil mapping in compliance with the tool in just a moment, but we recognize that many people maybe have never seen this before. So the goal is to produce something like what you see here on the left. This is a map produced by Perennial, and what you're looking at is a few agricultural fields in the calendar year 2022. You can see the field boundaries are outlined in gray, and then the colors in there correspond to mapped soil organic carbon stock in units of tons per hectare, where the blue values are lower and the more yellow values are larger. You can see how soil organic carbon stock varies spatially within individual fields, and you can also see how it varies between fields. Some fields that have more yellow or some fields that have more blue. If you could zoom in on this map using like a pinch zoom like you do on a smartphone, what you would see is that the map is made up of a bunch of individual pixels. In this case, each one of those pixels is a 10 by 10 meter square. And every one of those pixels contains a number. And the number for that pixel is the size of the carbon stock on average within that 10 by 10 meter square. The purpose of digital soil mapping is to build a statistical model that allows you to make a map like this. You then use the map to estimate the carbon stock, and when you do it at multiple time points, how that carbon stock is changing over time. What you can see in the lower right of the slide here is a map of carbon stock over time for this same area. Now what each dot represents is the average carbon stock within the whole area, and you can see it bounces around a little bit from 2014 all the way up to 2023. The blue dot highlighted there at 2022, that's the average of the image that you're seeing on the left. By using digital soil mapping, we can characterize how organic carbon stocks vary spatially within fields and across big areas using a vastly larger amount of data and information. And that increase in the amount of data and information is what allows the technology to bring real value. This increase in information content allows us to estimate soil organic carbon stocks and how they are changing over time with less uncertainty than would be required under, say, existing quantification approach 2, measure and remeasure, which is dependent on the existence of physical soil samples. If you go to the next slide, you'll see what the conclusion of digital soil mapping is. Where we want to get is something that looks like this. These are 3 example uncertainty deduction scenarios, and these are shown in Appendix 6 of the tool. We developed a computer code appendix that allows you to reproduce all the calculations in the tool using a data simulation. Data simulations are useful because they allow us to demonstrate that the tool does what we think it should do under conditions that we definitely understand. We also wanted to provide people with code examples in one programming language so that they would understand precisely how to implement the equations that are in the tool. This is simulated output here, and what it shows you is what the uncertainty deduction is that you would get under the conditions of the simulation. You can see we get all the way to a change in organic carbon stock over time, and that's what's indicated there on the x-axis. And the uncertainty in that estimate is what is reflected by that distribution that looks like a bell curve. You can then see what the uncertainty deduction would be for 3 hypothetical projects, each of which has a different duration of time associated with it, going from 18.4% down to 6.1% on the right. Now, in the real world, the actual uncertainty deduction you get will depend on the quality of model that you build, the size of the project that you have, and also the time duration. So this is simply meant to be illustrative. The point I want to make here, though, is that nothing about the tool changes how this uncertainty deduction is calculated. The tool is fully compliant with existing understanding of what an uncertainty deduction is and what a carbon credit is under, for example, VM42 or VM32. The only thing that's changing is how you get to that point. You can think of this as either an augmentation to quantification approach 2 or 1, or as something of an independent quantification approach that provides a new way. Next slide, please. I want to describe the goals and the motivation before getting into key components and then describing use cases. When we asked ourselves why we were doing this, we had these 3 goals and motivations in mind. First, we wanted to increase the value of intensive soil sampling. As I described to you a few moments ago, you can think of digital soil mapping as being like soil sampling, but you're doing it digitally rather than going out into the field, and you're doing it on a grid, where the grid might be 10 by 10 meter pixels. Soil sampling is difficult. It's logistically challenging, there are time constraints, and it's expensive. So one way to think about digital soil mapping is that it's a kind of augmentation of the process of soil sampling using a digital approach. We can take samples, and the tool does require their use, and allows them to be integrated into a digital soil mapping model that allows us to squeeze more value out of those samples. So that's number 1. Number 2 is we wanted to broaden the geographic scope of existing VCS methodologies. Biogeochemical models aren't available for many conditions around the world. Digital soil mapping is more portable, and it therefore has a potentially wider range of use cases that can allow it to be used in places where biogeochemical simulation cannot. Finally, we wanted to find a way to make digital soil mapping compliant with existing biogeochemical models. This is quantification approach 1, and therefore to strengthen their use. Next slide, please. The key components include validation with safeguards, and I'll describe to you what those safeguards are in a moment. We describe how to calibrate and also how to validate a digital soil mapping model. We are agnostic about the use of a very wide range of inputs, or what we call covariates, in the tool. These inputs can include remote sensing data, but also other environmental data, things like temperature, precipitation, elevation, crop type, tillage status, whether cover cropping was done or not. All of these things are open, and we provide guidance in the end of the tool in the appendix I described earlier that lists lots of examples of situations where people have used a wide range of different kinds of covariates to build digital soil mapping models. And final key component is that we use geostatistics, and geostatistical methods are core in the application of the tool for how we calculate the variance in SOC stock and the variance in how SOC stock is changing over time. We believe that the use of geostatistics adds an increased level of rigor. It's something that we're proud of. We provide guidance in the tool about how to do this, as well as in the code appendix. I'd like to talk to you now about use cases on the next slide. Use case number 1 allows digital soil mapping to be used with quantification approach 1, which is a process-based biogeochemical model. This is the measure and model approach. The idea here is that DSM model validation would occur at project start and then at least once every 5 years. Now, I want to be clear here, and I'll remind you of this in a moment. When I use the word DSM model validation, that doesn't mean the same thing as project validation. That's an important distinction that's easy to miss in the tool, but they don't mean the same thing. So what we're saying here is model validation would occur at project start and then at least once every 5 years, which is consistent with other VCS program rules. There's information in Appendix 5, and we specifically ask people to give us some feedback about how we are describing the integration in Appendix 5. On the next slide, I'll describe it to you now. There's two ways that we envision digital soil mapping being integrated with a biogeochemical model. One is point-based, and the other is area-based. The point-based approach uses the predictive distribution for each prediction support unit. That's a technical way of saying every pixel and the uncertainty associated with that pixel is used and then follows procedures that are very much like the existing Monte Carlo error propagation procedures described in VM42. The other approach is area-based, and this would allow a person to run a biogeochemical model not at the point level, but for an area, like a stratum, a field, or a collection of fields. And in that case, one would use the predictive distribution of the mean SOC stock at a given time. This predictive distribution is calculated in the tool and using geostatistical methods, which are described in the code appendix that I've described for you before. It's really important that we get feedback on what's in Appendix 5 from members of the community. We want to know whether the two approaches that are described are clear enough and whether you feel like they would meet your needs. Next slide, please. The second use case describes digital soil mapping as a direct measurement source. So here, we're not integrating digital soil mapping with a process-based biogeochemical model, but using digital soil mapping directly at time 0, time 1, time 2, calculating the differences in SOC stock over time using digital soil mapping, and then using that as the basis for generating the credit and calculating the uncertainty deduction. Again, as before, model validation occurs at the project start, and then at least once every 5 years. You can think of this as being very closely related to existing quantification approach 2, except that rather than using physical soil samples, you're using digital soil mapping to get the estimate of SOC stock. That's great. Next slide, please. I'd like to now walk through the process of how the tool works. This figure appears in the tool in more detail, and we provide a detailed description of all of its components. But what I'd like to do is just walk through by referring to the numbers and allow us to get on the same page about what each of the steps in the process is. So one begins over here at step number 1, where you can see those squares on the far left with dots on them. Those represent fields. And we go out into these fields and we collect physical soil samples. These are those black dots. The physical soil samples get sent to a laboratory and one gets back an estimate of SOC in percentage by mass. And that's what's shown in 1. So we have a data table where each row represents a soil core. And then there's SOC percentage, there might be bulk density, and then a bunch of covariates. The covariates could include remote sensing, temperature, precipitation, elevation, crop type, and so on. We provide guidance in the tool about the kind of covariates that one might want to use. Then we go to step 2. Here what we do is divide the data into 2 groups called training and test. This is a very standard process in statistics and in machine learning. The idea is that you develop a statistical model on one data set called the training data set, and then you test it on a different data set called the testing data set. The important point is that the training data set and testing data set are separate from each other. That way, when you do the test, the model is being tested on data it has never seen before. In the tool, we talk about how to do this using an approach called cross-validation, which is where you iteratively split the data into training and testing subsets. So for example, if you had a data set that had 1,000 points in it, you might take 900 of those points at random and use them to train, and then set aside 100 for testing. Then you take a different 900 and train and a different 100 for testing. And you repeat this until every point has appeared in both the training and the testing sets, each time generating a prediction. That happens in step 3 and step 4. And where you end is over here at 5. You have an observed SOC stock, that's the left column, and then you have a predicted SOC stock, and that's the center column. Note that in each case, the prediction of SOC stock for that point was derived from a version of the model that did not have that point in it when training. So independence is maintained between training and testing data. In the tool, we describe that you don't have to do it this way. You could have independent training and test sets if you wanted to, but most people prefer to do cross-validation because it's statistically rigorous, well understood, there's strong precedent for it, and it allows you to make use of all the data that you have, as opposed to having a completely set-aside test set. If we go to the next slide, we can talk about the 3 validation steps with safeguards. So first, coverage. We want to see that at least 90% of the independent validation observations fall within 90% prediction intervals. A prediction interval means that when we generate a predicted value for a point in the test set, we don't just create one number. We create one number with a range around it, and that range is a plus or minus. We describe in the tool how to calculate that range as a 90% prediction interval, which in plain language means we can be 90% confident that the true value really does fall within the range. We want to see, the tool requires, that at least 90% of the independent validation observations do in fact fall within the 90% prediction interval for the prediction. The next test is called an R-squared test. Sometimes this is called a coefficient of variation. R-squared asks how much of the variation in the data can be explained by the model. The threshold we decided to use is R-squared needs to be greater than 0. Now that's a very low threshold, and some users might be wondering why the threshold's not higher. Let me explain why we selected R-squared greater than 0. When it's greater than 0, it means that the model's providing a more precise estimate of the mean than the validation data does. It means that the model is offering an improvement. In almost all cases, we fully expect that the R-squared will be much greater than 0, substantially greater than 0. And a person who moves forward with a model that has an R-squared that's just barely above 0 is likely to discover that there is so much uncertainty in their model that they can't use the tool effectively because the uncertainty deduction will be so large that there's no value that can be claimed. We think that's a good outcome. This is what we mean by validation with safeguards. If the model performs poorly, it should result in a large uncertainty deduction, and one should not be permitted to claim that carbon is being stored. So R-squared greater than 0 is objective because 0 is an objectively defensible number. And even a model that has an R-squared greater than 0 by any amount means that the model's doing better than if you didn't have the model at all. And that's the justification for the threshold. There are 2 footnotes in the paper where we provide references to peer-reviewed journal articles that explain why an R-squared threshold of 0 is appropriate. And readers, we encourage you to read those papers if you have questions about that. The third criterion is lack of bias. We want to see that the model doesn't underpredict or overpredict on average. And the way we do that is by asking whether the mean prediction error of the model is significantly different from 0 or not. And what the tool wants to see is that the mean prediction error is not significantly different from 0. We believe these 3 validation tests are necessary and sufficient to confirm that a digital soil mapping model is rigorous and can be used in the context of a VTS carbon program. If we go to the next slide, we can go now through additional steps in the process. So we just ended at 5. We do the coverage test, the R-squared test, that's 6 and 7, and then the bias test. Those are shown here from left to right. So for example, you can see in the image on the upper left beneath the number 6, the value falls within the 90% interval, as indicated by the vertical green line. But in the distribution on the right, the predicted value falls outside the 90% interval, so that point would fail. Some points will fail. This is expected. What we want to see, though, is remember that at least 90% of the points fall within the 90% interval, as indicated down there on the bottom, where we say at least 90% coverage. The R-squared test in the middle at number 7 explains observations to predictions. We want to see an R-squared greater than 0. Normally, this will be substantially greater than 0, but 0 is the threshold. And then finally, the bias test on the right. Here, we're looking at the distribution of model prediction error and asking whether that distribution is significantly different from 0 or not. The tool requires that the distribution is not significantly different from 0. Next slide. If the model doesn't pass, the tool describes procedures that users can follow to go back and reproduce the model to try to improve the performance of the model until it does pass. So it's not just a yes or no, but you do have to pass before you're permitted to go through to step 11. Once a calibrated model exists, a user would use the model to generate predictions like the ones I showed you before for those fields in the project and in the baseline scenario. We then use geostatistical methods at step 12 described in the tool to compute the variance of the mean of the SOC stock. Digital soil mapping can allow you to calculate the mean, but to calculate the variance in the mean at step 12 requires geostatistical methods. These are illustrated in the tool and also described with examples in the code appendix. What that then leads to is an estimate of SOC stock and its variance at one point in time. This whole process gets repeated at every time point, and then the estimates of the variance at each time point are combined using an equation in the tool that allows you to calculate the variance of the change in SOC stock over time, and it is that results in the application of the uncertainty deduction methods in, say, VM42. Next slide, please. I want to emphasize that the tool requires the use of geostatistical methods to account for the spatial component of the model prediction error. We think this is really important, and we think it's a critical component of the rigor that the tool brings to VCS carbon programs. In the tool, we recommend the use of methods developed by Wadu and Hoovelink, published in 2023, but we clarify that any valid method is allowed. We provide a link to the paper in the tool. Again, we describe the application of this method in the tool, and again, we include a code appendix that describes how the specific method can be applied. But I want to emphasize, what we say in the tool is simply that one has to deal with the geostatistical component of the model prediction error. Other methods that are valid are permissible, and in the appendix to the tool, we describe what we mean by valid. Next slide, please. I'd like to now walk you through the verification and crediting process. We specifically designed the tool and the procedures to support a very wide range of scenarios. What do I mean by scenarios? What we're trying to accommodate here is the real-world situations that actually come up. Not all fields or area in a project might be available for enrollment at year 0. The tool needs to be able to accommodate rolling enrollment, for example. Some users might wish to update their model frequently. Some users might wish to develop a model and then freeze its parameters. This is something we heard from members of the advisory group. So the tool needs to be able to accommodate both of those situations. We developed procedures in the tool that we described that we believe does accommodate all of these scenarios, and the tool works under a cumulative adjustment method that is described in VM42. This is not something that's new. I just want to clarify that the tool is compliant with this and that this cumulative carbon credit adjustment would be implemented when it is relevant. And I'll describe to you in just a moment what I mean by when it is relevant. Here I want to emphasize again, before we get to the next slide, the distinction between project validation and DSM model validation. Those words don't mean the same thing here. We tried to be clear throughout the tool by using the word DSM model validation as opposed to project validation so that it was clear which thing we were talking about when. What we're about to see is described in Figure 1, and then we provide additional examples of a very wide range of scenarios in Appendix 2 of the tool. Next slide, please. Okay, so here's one example of a project quantification lifecycle. We have different things that happen here represented in rows, and then we have years across the columns. So for example, you can see in year 0, project validation occurs. That's the green box, and the model is validated and soil samples are collected. That's the light pink box, and it says there 1,000. So what we're saying is that 1,000 physical soil samples would be collected here to calibrate a model. Now, in reality, we give guidance on how many samples might be necessary, but because the tool is outcome-based, which we think is a strength, the answer to the question, how many samples do I need? Well, it depends on what the situation is that you are in. You need enough samples to be able to pass the tests and be able to calculate SOC stock and its variance with enough precision that you can estimate the stock and have an uncertainty deduction that is small enough for the project to succeed. 1,000 samples from being added to a model that's already been trained across a large geographic area is very likely to be sufficient, but it will depend. Model validation occurs. That's the second pink box there in row 3. And then you can see we describe which documentation is required. There's a PDD, and then there's a VVB audit, and then there's an independent modeling expert assessment, all of which happen in year 0. Then nothing happens in year 1 or 2, but then imagine that the project proponent might wish to issue credits in year 3. We're trying to make it easy for that to happen while still ensuring the rigor of the tool. And I want to explain how we've done so. So what we show here is that there's a model recalibration that happens in year 3, and we said that there might be 100 samples there. In the tool, we provide guidance by saying that the number of samples used to recalibrate the model here is at least 10% of the number that were used for the previous validation. So that's why the number here is 100. But again, this is just a guide. There's the recalibration that happens in year 3. There's the monitoring report that's issued in year 3, and then a VVB audit. Then we go to year 5. At year 5, there's a large recalibration of the model. So another 1,000 samples are collected. You can see there's a model validation that takes place at year 5 that didn't occur at year 3. A cumulative carbon stock change adjustment would occur here in year 5, but only if credits have been issued in year 3. In the tool, we provide a footnote that describes a hypothetical scenario where a cumulative carbon stock change adjustment might be necessary. The idea here is to reconcile the answer you get at year 5 with whatever you thought was true at year 3. I want to emphasize to you that nothing here is new. This is fully consistent with what's already in VM42, for example. What we're trying to do, though, is give people the ability to issue credits in intervening years in a way that doesn't require a full model validation, but that nonetheless ensures that there are safeguards in place. The cumulative carbon stock change adjustment is that safeguard. I also want to emphasize that one doesn't have to issue credits in intervening years. So you could imagine a scenario where that year 3 is just blank. That would be fine. And in that case, there would be no cumulative carbon stock change adjustment necessary because there would be no need to reconcile year 5 with year 3. The reason why we are asking people to collect additional samples in year 3 if they would like to issue samples in intervening years is to try to limit the range of swings that could occur in the model. The cumulative carbon stock change adjustment is a conservative mechanism that will perform the reconciliation necessary. But I think probably we all agree that it would be better if a large change to what we thought was true weren't actually necessary. So by doing a retraining in intervening years, if credits will be issued at that time, what we're trying to do there is limit the range of outcomes that is possible and reduce the importance of the cumulative carbon stock change adjustment. We can go to the next slide, and I'll remind you that if you go to Appendix 2 of the tool, there's many more complex scenarios available. We tried to think through different things that might come up and give people a sense of the set of conditions that they might encounter in the real world. I want to emphasize to you that the tool was designed and these scenarios were thought through in order to maintain outcome-based rigor that's consistent with VCS methodologies requirements while providing the flexibility that users need to actually use the tool in the real world in compliance with VCS carbon programs. I'll just reiterate some of the examples of the kinds of real-world complexity that we think is important. Things like rolling enrollments, things like accommodating project proponents who might wish to freeze the parameters of their model, something we learned about from an advisory group member, and also accommodating those who do not. We want to accommodate those who only wish to issue credits once every 5 years, and also accommodate those who might wish to issue credits more frequently. But we want to do all of these things while maintaining a consistent standard that ensures rigor in the output of the tool. Next slide. I'd like to conclude by asking you for feedback before handing the presentation over to Carolina to conclude us for the day and opening it up to questions. It's really important that we receive feedback from members of the public that can allow us to make any revisions that are necessary to the development of the tool. The working group process that I've described to you has been extensive. We've worked on this for over 3 years. The tool has been through multiple rounds of review inside Verra, outside Verra, and then with this working group, including a very wide range of members that represent scientific expertise, private companies, a VVB, and other project proponents. The purpose of that was to get the widest possible range of viewpoints on the tool so that we could not be blinded by things that we might just not know about. That process continues here by asking you to provide comments on things in the tool. In particular, we'd like to know, is the tool explained clearly enough to be used by you or your organization? And if not, what does it need to have in order to become clear enough that you could use it, either you or your organization? Do you agree that the methods described in the tool are a step in the right direction that they bring the necessary level of rigor that would be needed to VCS carbon programs in order for you to feel confident in the application of the tool if you were going to use it. And then finally, this is an important question about geography. Is the tool usable in the locations where you work? We want you to think about the places in the world where you work, the crop types where you work, the kinds of people that you work with. This question, locations where you work, is meant to be a broad question that's asking you whether you feel like this thing is viable in the way that you need it to be. And if not, we'd like to hear from you about what needs to happen in order to make it usable in the locations where you do work. I'll now hand it back over to Carolina, and then I think we'll be happy to take questions from the audience.
Thank you so much, Jim, for this very technical and detailed explanation. I know it's a lot to digest, but we hope that with this overview can help you to provide feedback to the tool. I want just to do a few clarifications here before we move to the Q&A section. So you might wonder how this tool can be used under the VCS program. It's mainly initially focused on to serve the VM42 and 32. As you know, the version 1.0, it does allow the use of remote sensing. That means if the tool is approved, DSM it's eligible, only registered projects only. For VM42 version 2.0, also only for registered project. But as you know, this version does not allow the use of remote sensing. But once the tool is approved, DSM will be eligible pending approval of the tool, and we will issue a clarification document to that. The same for VM42 version 2.1, which is the one which is currently active, and also depending on the approval of the tool, will be a clarification document to allow the use of DSM under this version. And as you know, VM42, it's undergoing major revision, the version 3, which we hope will be released towards the end of this year, perhaps Q3 or Q4. And if the tool is approved before then, and then it will be automatically accepted the use of the tool on this next version. And same thing for VM32. Version 1.0 does not allow use of remote sensing, but if the tool is approved, there will be a clarification document to allow the use. And this methodology is also under revision, and will be the same as for VM42. If the tool is approved before, the tool will automatically be allowed on the next version.
Carolina, we have a couple questions in the chat about VM47. Would you be able to comment on that quickly?
I can't see the questions. Can you?
Just the question is, the questions are, will the tool be applicable or available for use with VM47?
That's something, at the moment, we have not envisioned that yet, but it's something to discuss with the forest team. We're gonna find this out throughout the next development phase, and there will be still opportunity to be used in other methodologies. But at this point, it's too early to say that.
Thank you.
Mm-hmm. I see we have few questions here on the chat, on the Q&A box. David, that's for you. I wonder if you have samples collected at a very high density in each field to validate your predictions, such as from 20 to 9 centimeters depth. I think the question is if that's allowed.
Yeah, so I think this was in response to the figure that we showed. And I don't want to spend too much time on that specific figure because that's just an example. In that example, we did not collect samples on those fields because we're just illustrating the concept. But when you apply the tool, you do need to collect those and you do need to validate. As for that specific question, yes, we validated that model. That is a larger scale model. So that is a DSM model that we made for the entire continental United States. And we calibrated and validated it on a diverse array of soils, ranging even wider than that for that geography. But that is not typically how the tool will go. There's sort of a couple different ways you can use DSM. One is the larger scale maps, and one is the super fine-tuned project specific. The tool deals with project specific application. And to the other questions that were asked and that I answered around the requirement of soil samples, yes, you do need to take soil samples on the project. And that is why, is because we are calibrating and validating, or in actuality, it's validating specifically for the project in question. And that provides a lot of portability, right? So instead of having to collect a validation data set ahead of time that represents exactly your project scenario, you can just take it to the project, validate for that project, which makes it easier to take this anywhere in the world into a bunch of different diverse practices and types of agriculture.
Thank you, David. So there's one here very easy to answer. It's asking if the recorder will be available. Yes, it will be available on Verra website and also in Verra YouTube channel. The next question is about the key quantification approach tool. I think it's user case number 2. When using this quantification approach tool, a DSM would require biogeochemical modeling.
No, it does not require biogeochemical modeling. So you can use DSM without a biogeochemical model at all. But we talked about biogeochemical models because we know that some people already use biogeochemical models and may want to continue to use them. In those cases, DSM can provide some value because it can provide the SOC stock measurement that is necessary to initialize the biogeochemical model, and can do so in a way that is less burdensome because you're using DSM as opposed to physical soil sampling.
Okay, thank you, Jim. The next question is, if we have a project that is running and there wasn't SOC stock measurements at time 0, does the tool provide some ability to estimate the initial soil organic carbon stock and then apply this tool moving forward?
So I think there's two answers here, one of which is a programmatic answer that I'll ask you to speak to, Carolina, and then the other one is about digital cell mapping. From a digital cell mapping perspective, you can definitely do that. One of the useful things about digital cell mapping is that the model can go back in time using covariates from the past. So, for example, you can use digital cell mapping to get satellite data or environmental data from previous years and then make the map that corresponds to those previous years. And that's something that people do. That's, in fact, what the slide that I showed you a moment ago that had the data going back in time to 2014, that's precisely what we did. Whether that's compliant with VCS program rules is a question that I can't answer, and I would have to ask you to speak to, Carolina, and might even require a more lengthy response. I don't know if you know off the top of your head.
Yeah, I think we can take that this as a feedback and then clarify in the draft in the next phase. The next question is, can you please summarize the main improvements and business advantage of this tool delivers to a project developer as opposed to just use quantification approach 1 without DSM?
Yeah,
Sure.
so the main point here is the soil sampling density of actual physical samples. And so if you're using quantification approach 1, that would be use case 1, where you first take your soil samples, you use those to calibrate and validate a DSM, you apply that DSM, and then you use that to initialize a process-based model instead of the soil samples directly. And what we find is that because you're going from a sparse array of samples to a spatially contiguous map, you can reduce the number of soil samples you need, which often ends up being the most expensive and laborious part of running one of these projects. So this is an augmentation to lower the sampling density on top of the existing approach with just QA1 without DSM.
Thank you, David. I have a question here for Jim. Can you discuss the requirement of validation sample time collections of 6 weeks? Is there any flexibility for programs that collect sample but run into winter weather and decide to collect samples after winter?
Okay, so what we were trying to do here was be consistent with existing VCS guidelines, which say that sampling should be conducted, the phrase used, I believe, is in the same season. Okay, that appears in, I think, VM42. And that's where that 6 weeks thing comes from. What we thought was, well, how do we say that in a way that's specific? Because seasons don't, mean the same thing around the world. One of the things I've told you we talked about was geographic representation. Some places have, winter, spring, summer, fall. Some places have wet and dry seasons, and where you are in the world is that word season is gonna mean different things. So we just decided that plus or minus 6 weeks, so a 12-week window centered on the date was the way to do it that was compliant with VCS program rules. I'm not sure if that fully answers the question or not, but that's what we were trying to accomplish.
Thank you, Jim. We're just going to take one last question. Is the model able to distinguish the impact of regenerative agricultural practices, for example, versus baseline change in soil organic stocks?
The answer to that question is that yes, it is, and that is something that will come out of application through comparison to baseline control, right? So if the model is if the model is not sensitive to those things, then it would not be able to tell you that there is a difference relative to baseline conditions. So the model needs to be built in a way with the right kinds of covariates that we think are sensitive to those practice changes. And that could be explicit. One could include cover cropping and tillage status, for example, just as examples. They could be actual covariates in the model, or it could be implicit by measuring things like, for example, reflectivity of the land surface at certain wavelengths is thought to be related to tillage status, and that would be a more implicit way of doing that.
Okay, thank you so much, Jim. Thank you, David. Thank you to the audience for participating today. We know it's very technical, this tool, but we really hope that this presentation can help you to understand it better. And we look forward to receive your feedback on the online forum. Thank you, everybody, and have a good day. Ciao.